Okay, for section 9.1, we're going to look at applications involving right triangles. So the really good news about this is most of this we've seen. So we're just kind of getting to practice stuff that we learned way back in chapter 7, which is kind of a breath of fresh air because the last two chapters have been pretty dense. So this stuff is, a bit review. It's not too bad, okay? So for topic 1, we're going to look at solving right triangles. And what we need to do is just kind of review some basic information about triangles. And the first thing we have to remind ourselves of is that the three angles of a triangle have to have a sum of 180 degrees. And please don't tell your trigonometry teacher that you don't know this at this point. You know this whether you know it or not, okay? So the three angles of a triangle have to have a measure of 180 degrees. Now, we can classify triangles based on really two bits of information, their angles or their side lengths, okay? So if we were going to classify triangles based on their angles, we would kind of have three classifications that we need to be at least a little bit familiar with. First, you can have what's called an acute triangle. That means all of the angles are less than 90 degrees. An acute angle is less than 90, so all three angles of the triangle would have to have measures less than 90. You can have a right triangle, and we've dealt a lot with right triangles. So again, don't tell me you don't know what this one is. A right triangle has one right angle. The other two angles are acute. And then you can have an obtuse triangle where one angle is greater than 90 degrees and then the other two angles are acute, okay? Now, if we were going to classify triangles based on side lengths, you can have what's called an equilateral triangle where all three sides have the same measure. And because all three sides have the same measure, all three angles are going to be the same. They're going to measure 60 degrees, okay? Now, you can also have an isosceles triangle, which you'll definitely see an isosceles triangle again, I want to say in 6.2. Okay, but the deal with an isosceles triangle is you have two sides have the same length. Okay, and that means the sides opposite or the angles opposite those matching sides are going to be the same. So you may see something that looks kind of like this. And let's say we mark with little tick marks that match. Okay, matching tick marks just mean matching sides, like the sides have the same measure. So we're saying, hey, these two sides have the same measure. Well, directly opposite from those sides, you have two angles. Those two angles also have to have the same measure. So that's an isosceles triangle. And then finally, we can have what's called an oblique triangle, and we're going to deal a whole bunch with oblique triangles in the next 2 or 3 sections. Those are situations where all of the lengths are different and all of the angle measures are different, so nothing matches. Okay? Now, a couple of things that are worth noting. First of all, I'm going to tell you something that's not like explicitly listed here. We get in the habit of labeling triangles, whether they are right triangles, like what we're going to deal with in this section, or oblique triangles, like what we're going to deal with in the next 2 or 3 sections. We have a tendency to label them the same way. We label the angles with uppercase A, B, C, and then we label the sides opposite the angle with the matching lowercase letter, okay? So in a right triangle, we always label the hypotenuse C. And so I'm going to go ahead and label the largest angle C. And what you need to know is the largest angle in a right triangle is 90 degrees, and it is going to be opposite the largest side. That is not an accident. So the largest angle is going to be opposite the largest side of the triangle, okay? Now we would label the other two angles capital A and capital B, okay? And opposite angle A is side length lowercase a, and opposite angle B is side length lowercase b. Okay, so just kind of get in the habit of that. All right, understand how we label these triangles. You're going to see this quite a bit. Okay, now I have a couple of pieces of information here. One we've already gone over. The largest or longest is probably what you should say. The longest side length is directly across from the largest angle. And the smallest or the shortest side length is always going to be across from the smallest angle. That is not an accident, okay? So when you're solving these triangles, you can look at the lengths of the sides and kind of order them smallest to largest and make sure their angles are in that same order, smallest to largest. And you'll know that you're at least on the right track, okay? And then finally, to solve a triangle means to find the length of all of the sides and the measure of all of the angles, okay? So for example, one, it says solve each right triangle, round all decimals to the nearest hundredth. So that's 2 decimal places. And example A is pretty easy, okay? Now, before we move on, I do want to give credit. I don't know who gets the credit, but I did not make these images. I stole these from another instructor. I copied and pasted because they had some really good examples. So kudos to them for being able to make these figures. Okay. Now for part A, it says solve the right triangle. So we know we have to have a right angle in here. Okay. So that tells me that C is definitely a right angle. Okay. You can never assume an angle is a right angle unless you are told explicitly that it is a right angle, because you could have something that's like 89.5 degrees or 90.14 degrees. It's going to be super, super close to 90, but it's not exactly 90. So you have to be told it's a right angle. Okay. Now we also know, so we know angle C, we also know angle A. And if we know two of the three angles, we can easily find the third. Okay. So we know that we have 180 degrees to play with to begin with. Well, we've used 90 of them on angle C. So that leaves me 90 degrees that I can split between angle A and angle B. So I need to find the measure of angle B. So all I have to do is take that leftover 90 degrees and subtract what has already been used for angle A. Okay, so angle A is 36.87 degrees. If you haven't gotten your calculator out, please do so. I will switch back and forth to my calculator app, but for something easy like this, we'll just trust the system, get your calculators out. So we have 90 minus 36.87, which is 53.13 degrees. So we know this angle right here is 53.13 degrees. Okay? So that was easy enough. We now have the measure of all three angles in the triangle. And luckily we were given the length of two of the sides of the triangle, but we have to find the third. Okay, so let's do a little labeling here. Now, opposite side A is side length lowercase a, or opposite angle A is what I should say. Opposite angle A is side length A. Opposite angle C is side length C. And opposite angle B is side length B, and that's what's missing. Okay. And the great news is we're dealing number one with a right triangle, and two, we have two of the three sides. So we can just use the Pythagorean theorem to find our missing side. So the Pythagorean theorem, hopefully you remember, says take one of the legs and square it, add it to the other leg squared, and it has to equal the hypotenuse squared. Okay, so we know what A is. So A squared is 9 squared. B we don't know, so it's just going to stay B squared. And that has to equal C, or C squared, which is going to be 15 squared. We want to evaluate what we can. So I know that 9 squared is 81. B squared is just B squared for now. And 15 squared is 225. All right. I want to get the b squared alone, so I need to subtract 81 from both sides. So that gives me that b squared is equal to 144. And in order to get the value of b, I take the square root of both sides, and that tells me that the length of side b has to be plus or minus 12. But think about that. So we know when we're solving something like this, we do the plus or minus and we take the square root of both sides. But if we're dealing with the length of the side of a triangle, we can say with great confidence this is just positive 12. Okay, so with very little work, we were able to solve this triangle. We know the length of all the sides, we know the measure of all the angles. Okay, now the great news is we get to do not way more work, but we get to do a good bit more work for part B. Okay, so part B, again, the directions say solve the right triangle. So we know again that angle C is a 90-degree angle. And just like before, we know that we have 180 degrees inside the interior measure of those angles. They have to add up to 180. We've used 90 of it on angle C, so that leaves us 90 degrees to play with. Okay, now I know that angle B is 62 degrees, so I can easily find A. I've got 90 degrees to split between A and B. So A is going to equal 90 minus whatever has already been used for angle B. So 90 minus 62 is 28 degrees, and that is the measure of angle A. Okay, now we've got all the angles. Let's talk about the lengths of the sides, and this is where the extra work is going to come in. We only have one length that's been given to us, so we cannot use the Pythagorean theorem here. Even though we have a right triangle, we don't have enough information to use the Pythagorean theorem. So we're going to have to go back to right triangle trigonometry. But first, let's go ahead and label the remaining sides of this triangle, or not the remaining, the three sides of this triangle. We'll label all three of them. So opposite angle A, we have side length A, which is currently missing. Opposite angle C, we have side length C, which is the hypotenuse, but also missing. And then opposite angle B, we have 7. So we know the length of side B, okay? We need to find side A and C. Now, the good news is you are trigonometry students that are halfway through, well, a little less than halfway through your course. So we can go back to what we already know. We have already talked about right triangle trigonometry. We did this way back in chapter 7. So we are already familiar with SOHCAHTOA. All right, so remember that means sine of some angle is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Let's use as much of that, let's use that information to solve for these two sides. So you kind of just have to pick and see if you have enough information to use these trig functions, okay? So let's start talking about side length C. Let's say we really want to find the hypotenuse, okay? And let's say that we are really attracted to angle B. You could use angle A as well. I'm just choosing to use angle B, okay? So we need to think about, okay, sine, cosine, or tangent of angle B. Well, I want to find the hypotenuse. So that means whichever trig function I want to use has to have a hypotenuse involved in it. So that limits me to sine and cosine, okay? And I need to make sure I have enough information to find this missing piece, which we're currently focusing on C. So let's talk about cosine first. Well, cosine relates the side adjacent to whatever angle, and we're talking about angle B now. Well, the adjacent side is missing, and it relates the adjacent side to the hypotenuse. Since both of those side lengths are missing, I can't use cosine. But I could use sine because sine relates the opposite side to the hypotenuse. So let's talk about sine of 62 degrees, okay? So if I'm looking at sine of 62 degrees, that's going to equal the side opposite that angle, which is 7, over the hypotenuse, which is unknown, but we're going to go ahead and call it C. And believe it or not, this is enough information to solve, okay? If I multiply both sides of this equation by C, I'll notice that on the right, the C's just divide out to be 1. 1 times 7 is just 7. So I end up with C times sine of 62 degrees, and that's going to equal 7. Well, remember, sine of 62 degrees is just some number. So I can undo this multiplication of C and sine of 62. So sine of 62 degrees, we're going to divide both sides by that. On the left, sine of 62 degrees divided by itself, that just becomes 1. So I'm left with just C. And C is going to equal 7 divided by sine of 62. So let's go to the calculator. All right, so make sure you're in degrees mode. I can see up here that I am. If your calculator doesn't display what mode you're in, hit the mode button, which is beside second, and it will tell you if you're in radians or degrees. If radians is highlighted, go down and then to the right until you're flashing on degree and hit enter, okay? And then second mode just takes you back to your home screen, okay? And I like to type in the fraction template. And there's a couple of ways to do it. I just tell my students alpha y equals, and then hit enter, and you get the fraction template. My numerator, 7. My denominator, I'm looking for sine of 62 degrees. And then we wanted to round all of our values to 2 decimal places, so hit enter, and we get 7.9, if we round up 3, so 7.93 here. So that tells me that the length of the hypotenuse is 7.93. Now we need to find the length of side A, okay? And you have a few things up your sleeve. We have enough information now where we could technically use cosine of 62 degrees. We could also do the Pythagorean theorem, but I hesitate to do either of those because both of those would involve C. And keep in mind, we just rounded C. 7.93 is not exact. This is approximate, okay? And we usually put the little squiggly equals to tell the reader, hey, we've rounded. So what happens with rounding is you get a little bit of error. And if I use a rounded value in another formula, I get even more round off error. And then if I use it again, I get even more round off error. So you kind of end up compounding this round off error. So anytime you're dealing with stuff like this, if you can use exact values, use exact values, okay? So for me, I'm going to stick with angle B, Okay, you could certainly do this with angle A. It would change things a little bit, but the answers would ultimately be the same. But I'm going to stick with angle B. And in order to find A, I'm going to go with tangent because tangent relates the opposite side, which is exactly 7, to the adjacent side. And I don't have to deal with this like round off being compounded, like using a rounded answer in another formula. Okay, so I'm going to look at tangent of 62 degrees. It's going to equal the side opposite that angle, which is 7, divided by the side adjacent to that angle, which is A. And then we're going to solve pretty much the same way we did in the previous example. So we're going to multiply both sides by A. On the right, the A's just divide out, leaving us with 1 times 7. So I get A times tangent of 62 degrees equals 7. Well, I can divide both sides by tangent of 62 degrees because that's just some number. Tangent of 62 degrees divided by itself is just 1, leaving me with just 1 times A. So A is going to be whatever 7 divided by tangent of 62 is. So let's go back to the calculator. Again, I'm going to go alpha y equals and choose option 1. My numerator is still 7. And then for the denominator, I get tangent of 62. And we get, if we round 2 decimal places, 3.72. So let's go back to the worksheet. And we're going to say that the length of side A is 3.72. So 3.72. Now let's think about this just a little bit. We talked earlier very briefly about how the largest angle is going to be across from the largest side, or the longest angle, or the largest angle is going to be across from the longest side, and the smallest angle is going to be across from the shortest side. So if I were to put my sides in order, I would get A, which is 3.72, then I would get B, which is 7, then I would get C, which is 7.93. And let's see if our angles line up in that correct order. The smallest angle is A, which is 28, and it goes with its opposite, the 3.72 side. The next angle is 62 degrees, which is opposite that middle side, which is 7. And the largest angle is 90 degrees, and it is opposite that longest side, which is 7.93. So you kind of want to always make sure that's happening with your work, okay? All right, one more example. So we're going to look at an applied example. Can't speak. So example 2 says solve and include units with your final answer, round values to the nearest hundredth. Okay, so 2 decimal places again. So this one says a surveyor can measure the width of a river by setting up a transit at a point C on one side of the river and taking a siding of a point A on the other side. So that's kind of what's happening here. Let's change colors. So we have this point C. So this is where the surveyor starts. They set up their transit and they take a siding directly across the river to this point A. Okay, so they're facing A, they take a siding. They then turn 90 degrees and walk 300 meters. So they make a 90-degree turn basically. Okay, so they turn through an angle that's 90 degrees and then they walk 300 meters to point B, and then they take another siding and it gives them this angle. So this angle right here, we are told, and again, I stole this problem from somebody else, and so you can see where they've like blacked out this problem and written over it, which I think is cute. But anyway, so we've got 300 meters from point C to B, and we know the angle from that B is creating here is 25 degrees, okay? So we want to use all of this information to see if we can figure out the distance across this river, which is essentially the length from C to A, which they've labeled it B, okay? And that kind of makes sense because this is uppercase B, this is lowercase b, and they're opposite one another. Okay, so considering this angle of 25 degrees, we are looking for the side opposite, and all we have right now is the side adjacent, okay? So when you're dealing with opposite and adjacent, you should think tangent, okay? So tangent relates the opposite side and adjacent side. And please remember, tangent is quite literally opposite over adjacent. Okay, so if we wanted to solve this problem, we would say, okay, we're going to take tangent of this 25-degree angle. It's going to equal the side opposite, which we have labeled with a lowercase b, and it's going to be divided by the length A, which is 300 meters. And then we want to see if we can solve for B. So I like to get rid of my fractions. I don't want to deal with a fraction if I can handle it. So I'm going to multiply both sides here by 300. And what happens is the 300s on the right, they just divide out to become 1. 1 times b is just b. So I'm going to write my b first. And then b is equal to this mess right here, which is 300 times tangent of 25 degrees. Now, you could have certainly figured out that this angle right here is what? 25 plus, that's going to be what, 65 degrees? And you could have done this with angle A, but that would just require more work. So just use the information you're given here. So we want to take 300 times tangent of 25 degrees. Let's go back to our calculator. Now, I know I'm in degrees. Make sure you are too, okay? So we want to take 300 times tangent of 25 degrees. And we get, if we round 2 decimal places, we get 139.89. So 139.89. And don't just leave it 139.89. I don't like naked numbers. 139.89 what? Okay. Well, in this case, meters. So 139.89 meters. And then I would describe what my meters mean. Is the distance across the river. All right, and that's your final answer. Okay, so in the next video, we're going to talk about solving right triangles, where we get to do something really, really fun, where we get to use inverse trig functions. Okay, so kind of start thinking inverse stuff.